Okay, let's take a look at WebAssign, section 8.3. So number 3. So we have a subset of Z. Now, didn't we talk about this in the office hour a little earlier in the week?
Yes, but it kept the first equivalence class kept turning up wrong, and also the last question, the list of distinct equivalence classes of R, those two problems kept on coming up incorrect, and I wasn't sure why.
Okay, so let's try to find the equivalence class of 0. Now, how are you finding elements of the equivalence class? Like, what is your algorithm? And are you using set brackets?
Yes.
Okay, good. Well, we know for sure 0 is in there because every element that names the equivalence class is related to itself, right? No matter what the equivalence relation because of reflexivity. So you can always start by putting the element that names the set into the set, right?
Yeah.
I mean, 0 has to be in its own equivalence class because 0 has to be related to 0 because it's reflexive. And think about it. What is 0 minus 0? If both x and y are 0, what is 0 minus 0?
0.
Is it true that 3 divides 0?
No.
Well, it is. Let me just show you. Here's a couple of facts to know. N divides 0 for any non-zero integer n. Why is that true? Well, it's because we can write 0 as being equal to n times an integer k. What's the integer k that will make that true no matter what? What can we multiply n by
0.
to get 0?
0.
Right. So no matter what the divisor is, call it n, call it d, that'll divide into 0 because of this. Okay? Now, do you remember when we talked about congruence mod 4? The way that we did it was we jumped by jumps of size 4 to get between the elements.
Yeah, I remember.
Well, our jumps are going to be size 3 now because the only way that x and y can be related, mod 3 or congruent mod 3, is if the distance between x and y is a multiple of 3. 3 divides it. So that means these are either 0 apart, because that's a multiple of 3, it's 3 times 0, or these are 3 apart. 3 is a multiple of 3, because 3 is 3 times 1. Or maybe these are 6 apart, because 3 divides into 6. Or maybe these are 9 apart, or 12 apart. You see what I'm saying?
Yeah.
So we're going to jump by jumps of size 3. So what is going to be related to 0 from this set that they have given us? Now, your set might be slightly different, okay?
Okay.
But for this set, what would be some other elements that are related to 3? To 0, excuse me.
3
Yep, 3.
and
Because if
6.
you put, right, and what else?
I think that's it.
What about 6?
Oh, yes, other than 6, that's all.
Yeah, because it's, look, the distance between 6 and 0 is 6, right? 6 minus 0 is 6. 3 divides 6. Or if you put the 0 first, 0 minus 6 is negative 6, but 3 divides negative 6 too. And the distance between 3 and 6 is 3. So everything in here has to be related to everything else. These are all separated from each other by jumps of size 3, okay?
Okay.
Now, how about 1? What's the first element you could put in there and be sure that it's related to 1?
Is it 4?
4 is definitely in there, but so is 1, because 1 is related to 1 because it's an equivalence relation. And 1 has to be in its own equivalence class because it's related to 1. Because 1 minus 1 is 0, and we already know 3 divides 0. But yeah, so you see what I'm saying?
Yeah.
4 minus 1 is 3, and 3 divides 3, so 4 is sure in there. What else is in there?
7.
Yep, because it's 6 away from 1 and it's 3 away from 4. What else is in there?
Is -2 also in there?
Absolutely. Because if you put 1 here and -2 here, 1 minus -2 is 3. 3 divides 3, right? The distance between -2 and 1 is 3. The distance between -2 and 4 is 6. The distance between -2 and 7 is 9. Those are all multiples of 3. Good. How about 2? What's going to be in its equivalence class?
5 and
2.
-2, -1, and 5.
I'm sorry. Are you saying -2 is going to be in the same equivalence class with 2? But it's in the equivalence class with 1. It can't be in 2 different equivalence classes because the equivalence classes partition up the set. So each of these elements will be in 1 equivalence class.
Yeah, so would it be -1 and then 5?
You're missing an element that should always be in the class that's got this name.
Yeah, so it should be 2.
Absolutely. Now, this is interesting because this brings us to the fact that sometimes you can just name the same equivalence class with 2 different names. See, the equivalence class of 0 had 3 in it. So that means it's the same as the equivalence class of 3. They're also both the same as the equivalence class of 6. So what goes into the equivalence class of 3?
3 and 6.
Okay.
Oh yeah, 0, 2. 0, 3,
And
and 6.
0 as well, yeah. So there are really only 3 equivalence classes, mod 3, but here they've just shown us that you could call them different names because you can take any of the elements as the representative to name the equivalence class. For example, the equivalence class of 1 could be called the equivalence class of 4, or it could be called the equivalence class of 7, or it could be called the equivalence class of -2. They're all the same equivalence class. And if you check the class notes, you'll see that. Okay. We
Okay.
talked about that, how you can take any element of an equivalence class and use it to name the equivalence class. All right. Now it says, how many distinct equivalence classes does this relation have? What do you think?
3.
That's right, 1 for each remainder. And in fact, we traditionally use the remainders as the representative to name the class. We usually use 0, 1, and 2. We don't actually usually use 3 or 4 or 5 or 6 or -2 or 7 or anything like that. We usually use the remainder. And now it says list the distinct equivalence classes. Well, you can just take this, select it, Control C if you're using a Windows computer. I suppose there's a cut and paste option with an an iOS operating system, but Control C, Control V, and you would just cut and paste these 3 different equivalence classes. Put commas between them. It's a comma-separated list of sets. On the worksheet, I asked you to do something slightly different. I asked you to build the partition, in which case these would be the partitioning sets like A1, A2, and A3. You might call them A0, A1, and A2, actually. And you would put these inside set brackets if you're building the partition. But here we're just listing the elements of the partition. Does that help?
Yes, that helps. Okay.
This one's not as intuitive. Number 4 is not as intuitive, but what you need to do is just do the algebra. If you want to figure out what elements are related to each other, then we need to do that maybe on paper, because this one's not as intuitive as jumping by jumps of size 3. Okay, so let me just write this down. This is problem number 4. And A goes from -7 to 3. And for all M and N in A, M is related to N if and only if 3 divides the difference not of M and N, but the difference of their squares. So let's write the elements of A down so that we can play this game. We'll do a few of them, but we probably won't work through the whole thing, but we can certainly try to get started because we have to figure out the equivalence classes. Okay, and because we're asked to list the equivalence classes. So, I mean, we can start with 0. All right, remember, 0 has an equivalence class. That's what this notates, these square brackets. So the equivalence class of 0 is the set of x in A such that 0 is related to x. But that also means that 3 divides 0 squared minus x squared. Or you could think about it as 3 divides x squared minus 0 squared. You can use either one of these definitions because it's a symmetric relation. It's an equivalence relation. You see, if 0 is related to x, then x has to be related to 0 by symmetry. So that's why I'm saying you can use either one of these for your definition. So let's just check. We want to look at the x's and see which x's satisfy 0 squared minus x squared is divisible by 3. Well, 0 squared is 0. What's 1 squared?
1 squared is 1.
Okay, let's figure out all the squares then. What's 2 squared?
Two squared is 4.
Good. 3 squared.
9.
All right. Now let's keep going. Let's look at all of these elements. What's -7 squared?
Positive 49.
Yep. And what's -6 squared?
Positive 36.
Good. What's -5 squared?
Positive 25.
All right, we'll just keep going. Let's do them all. (16, 9, 4, and 1, right? These are our perfect squares if they were positive. Okay, so we need to put together the numbers that are separated from each other still by jumps of size 3, but it's not the numbers. I said the numbers that are, I mean the numbers whose squares are separated by jumps of size 3. So let's think about 0. Which of these numbers is separated from 0 by a multiple of 3?
3 squared.
Good. So we're going to, and what about 0? Remember, 0 will be in there too, right? Because 0 squared minus 0 squared is 0, and 3 divides 0. So always start with the element in the class, just so you don't forget it. And so 3 squared, so 9 is, so 3 squared puts 3 in there. Yep. What of these other numbers are away from 0 by a multiple of 3?
-6.
Yeah, so -6 is going to go in there.
-3.
Yep, -3.
And then would +1 and -1 go in there, or
Yep, they're both elements of this set. So and they are jump size 3 apart from each other, right? You can get, right? They're 6 apart, right? And 0 and -6.
Mhm.
But anyway, what about 1? We're looking for elements from this set whose squares are apart from 1 squared by jumps of size 3, because 3 needs to divide their difference.
So you would get
What's the first element you should put in there, no matter what?
0, 1.
Exactly, 1. 1 is related to itself because 1 squared minus 1 squared is 0 and 3 divides 0. All right. What else?
-2.
Yeah, because -2 squared is 4, and you can get from 1 to 4 by a jump of size 3. So -2 is definitely in there.
And then -5.
-5, because 1 minus 25 is 24, and 3 definitely divides 24. So -5. There's one more that's in there that I can see.
Is
Oh,
it
2
0?
more. There's 2 more in there.
Oh, I'm not sure.
Well, check them. All right. We're looking at 1, right?
Yeah.
So let's check 1 against 4. What's 1 minus 4? 1 squared minus 2 squared. What's 1 minus 4?
-3.
And doesn't 3 divide -3?
Yeah.
So 2 needs to go in there. Does 9 go in there? Does 3 go in there? Let's just check it. Well, no, because it was in this equivalence class, but you can also check it. 1 squared minus 3 squared is 1 minus 9. That's 8, and 3 does not divide 8. So that's, verification that 3 isn't going to be in the equivalence class with 1. It wouldn't be anyway, because it's already been found to be in the equivalence class with 0. All right, let's check 49. 1 squared minus -7 squared. So it's 1 minus a 49, which is -48. Does 3 divide -48?
Yeah.
Okay, 3 divides -48 because it's 3 times -16, right? So we're going to put -7 in there. And you can check to see if -6, oops, -6 is in with 0, so we don't need to worry about it. We know it's not going to be in both. -5 we already found because 1 minus 25 is -24, and that's divisible by 3. What about -4 squared? What's 1 squared minus -4 squared? That's 1 minus 16.
That's -15. That's also divisible by 3.
It's -15. That's right. So -5 is in here. Excuse me, -4. Oh, my bad. That was -4 because that was 16. My bad. We already had -5 in here. It's in there too, but we're talking about -4 here. All right, let's see how many elements we have. We've got 0, 1, 2, 3. We've got, do we have -1 yet? Ooh, we don't have -1 yet. Oh, but what's -1 squared?
+1.
Yeah, so 1 squared minus -1 squared is 1 minus 1 is 0. Does 3 divide 0?
Yes.
So we're going to put -1 in here as well. And that's all of them. All of these belong in one of these two equivalence classes. There's only two equivalence classes. Do you remember we had some results that we proved? And one of the results we proved was that when you divide a perfect square, it's not exactly the same thing, but perfect square, when you divide it by 3, you can only get remainders 0 and 1. You can't get a remainder of 2. But anyway, these are the two equivalence classes, okay? So
Okay.
if we go back and look at, it says, use set roster notation to list the equivalence classes and enter your list as comma separated list of sets. So you would put, these two sets, you would put the equivalence class of 0 would have like 0, 3, -6, -3. It doesn't matter what order you put those elements, comma, and then the other equivalence class that's got all those other elements in it. Does that make sense? You'd finish that. Okay,
Okay, sounds good.
good. All right, next question from somebody else now. Let's give somebody else a turn. Those were good questions from what assigned to look at.
I have a question on 1B on the chapter 8
Okay,
the worksheet. I said review.
sure.
1B. I didn't get the part where you said find a row that describes G.
Oh, okay. Let's take a look at that one. I was wondering how folks would do with that particular one. So let me just open up the worksheet so that we can look at this. So 1B. We've got, it's a binary relation from X to Y, okay? So the worksheet in chapter 8. I'm not still sharing the screen, am I?
No.
So X has 1, 2, 3, 4, and 5 in it. And Y has 1, 2, 3, 4, 5, and 6 in it. And we defined a binary relation G from X to Y. So here it was 1, 3, 2, 4, 3, 5, 4, 6. Notice it's definitely not even a function, right? Not every binary relation from X to Y is a function, right? Because a binary relation is any subset of X cross Y. This is sure a subset of X cross Y, but it's not a function because 5 does not appear as a first coordinate of an ordered pair. Okay, so as you look at these, do you see a relationship between the first and second coordinates at all?
They're like jumps of 2.
Yes. So X is going to be related to Y if and only if Y is equal to X plus 2. Or you could say X is equal to Y minus 2. That's it.
Oh.
That's that simple.
Okay, thank you. But Okay, for part A now of that same question,
Uh-huh.
and it says X and Y are elements of the relation, even only if X and Y have a common prime factor.
If they,
Um,
yeah, right. So
so
X,
go
Y
on.
is in the relation if and only if X and Y have a common prime factor. Good. Keep going.
So I'm not just writing the prime numbers that are in those sets X and Y. I'm pairing them if they have the same prime factors, regardless of if they're non-prime numbers.
That's right.
Okay.
And notice 1 is not going to appear as a first or second coordinate because it
Right,
doesn't have any prime factors at all, right?
right.
So we can go ahead and build this thing. We know 1 doesn't have a prime factor, so it can't be related to anything, but 2's got a prime factor, right? What are the prime factors of 2?
2.
2. So when we go over here, we're going to pair 2 up with any of the elements here that have 2 as a prime factor.
Okay.
So what would we pair 2 up with? There's a bunch of them.
The first one will be 2,
Good,
and then we have 2 comma 4
good,
and 2 comma 6.
good. Now we move on to 3.
And
Or you can also realize, you see, the thing about it is these aren't the same set. These aren't the same set, so we have to be careful. Like
okay.
6 and 2 have the same prime factor of 2, but 6 isn't even in X. So 6, 2 can't be in here. Does that make sense?
Yes.
But 4, when we get to 4, it's going to be related to 2 and to 4 and to 6.
Okay.
Okay. But since it's from X to Y and not just on a set X or on a set Y, let's just be methodical. Let's move on to the next number that can be a first coordinate, and that's 3. All right,
3.
so what are the prime factors of 3?
We have 3 and 3
Okay, so 3,
and
3,
3, 6.
good. All right, now let's move on to 4. Its only prime factor, of course, is 2. So what will we pair 4 up with?
4,
4 will get paired with 4. What else?
2,
Yeah, 4 needs to be paired with 2,
and 6.
and 4 gets paired with 6. Good. And then finally, 5. 5 has a prime factor, doesn't it?
Yes. 5.
And so that's the only one it can pair up with.
Yeah. All right. So even if it says for every X and every Y, and 1 is a member of X and Y, we can build the sets without including 1 since it doesn't have a prime prime factor.
That's right. Because the reason we say for all X and Y, for all X and all Y and Y, the reason we say that is this rule applies to all the X's and X and Y's and Y's.
Okay. All right.
All these rules are always universal. They apply to all the elements. So that's sort of a formality. That's why I didn't even write it here.
Okay. All right. Thank you.
Uh-huh. Next question.
I had a question from test 3.
Uh-huh.
Yeah, because I was so confused about the GOF, finding G of F.
Okay, let's go to test 3. Let me just grab it. So which problem number was it again?
That was problem number 4.
Putting the problem number 4. Okay, so test 3, problem 4. Thank you. That helps. All right, so in this particular problem, we had 3 sets. X has 1, 2, 3, 4, and 5 in it. Y has 6, 7, 8, 9, and 10 in it. What's in W?
W has 2, 4, 6, 8, and 10 in it.
Good. And f is a function that goes from x to y. What are the ordered pairs in f, please?
In F, it's 1, 10, 2, 8, 3, 7, 4, 9, and 5, 7.
Good. And g is going to be a function from y to w. What is in g, please?
6, 4, 7, 4, 8, 8, 9, 10, and 10, 10.
All right. So we want to find the construction g by way of f. And notice g of f starts with f, so it maps out of x, goes into y, but then g picks up elements from y and maps them into w. So the way to think about it is like this. F happens first, okay? So here's f. It's like a little function machine, and we drop in an element little x from set x. Well, out comes f of x, which lives in y, right? The image of elements under function f are elements of y. And then that gets dropped into the function g, and out comes g of f of x, which is what we call g of f of x, okay? So there are a couple of different ways to draw pictures that can help you with this. Two different ways I can think of to do it, okay? You can draw a picture this way, where you draw the arrow diagram for f and for g. So f maps out of x into y. Okay, so f is going to do that. And then g is going to pick up and map out of y into w. And we can draw these elements. There's another way to do it, okay? I just want, this way takes quite a bit of time, but it might be worth it if it's not intuitive to you. You know how to draw these arrow diagrams, right?
Yes.
So you can draw the arrow diagram that says what f does, right? F sends 1 to 10. And it sends 2 to 8. And it sends 3 to 7. And it sends 4 to 9. And it sends 5 to 7. Right? And then G picks up and sends elements from Y over into W, right? 6 goes to 4. 7 goes to 4. 8 goes to 8. 9 goes to 10. And 10 goes to 10. So one of the ways, let's call this approach 1. Is just follow the arrows from each element in X all the way into W. Okay? So let's think about what happens to 1. 1 goes to 10. And where does 10 go?
To 10.
So that means 1 starts out there, passes through 10, and winds up at 10. Okay? See it?
Yeah.
All right, let's see what happens to 2. Where does F send to?
Sent it to 8.
To 8. And then where does G send 8?
Back to 8 again.
So far, it just doesn't look very different from F, but it will in a minute. What about 3? Where does F send 3?
It maps to 7.
Then what does G do?
It goes to 4.
So 3 winds up at 4. Now that's different from F. What about 4?
It maps to 9 and then goes to 8. 10, excuse me.
Uh-huh. To 10, good. And then 5?
It maps to 7 and then it goes to 4.
Very nice. So that's one way to do it. Okay? Another way to do it is to not, draw this, but to look at the mappings. It's more of an algebraic approach where you don't really need this picture. All we need are these ordered pairs. So let me show you how to, deal with it like that if you would prefer. Okay, so still we have to, you follow arrows. We are following arrows using the ordered pairs. Follow each element of X, because that's the domain of G of F. And we're still going to have to figure out. So 1 maps to 10 under F, and then 10 maps to 10 under G. So 1 winds up at 10. Okay, 2 goes to 8. You can just read the order pair. 2 goes to 8, and then 8 goes to 8. So 2 goes to 8, which then goes to 8 under G, right? 3 goes to 7, which then goes to 4. So 3 goes to 7, goes to 4. So we have 2, 8, 3, 4. See, you can do it either way, but you'll get the same G of F using either method. Oh, could you see that? You should have spoken up if that wasn't visible on the camera. I'm sorry. But did that make sense?
Yeah.
Good.
I also have like similar question, the question you give on the review for final exam last week, like. So it was like for A to D.
I'm sorry. From what?
The review for final exam. The last question you give like to practice.
I gave you, oh, you mean from the class notes?
Yeah.
Okay, let's take a look at the review for the final exam from the class notes. Good. So at the very end, well, in that one, we've got, it was a challenge, right? Where we've got F goes from A to B, where A had the elements 1, 2, 3, 4, 5, and 6. Can you see this okay? Because I'm looking at,
Yeah.
I've only got one monitor right now. And F was the set where 1 goes to A, 2 goes to B, 3 goes to B, 4 goes to E, 5 maps to E, and 6 maps to F. Okay, because it maps from A into B, and B was the set that had little a, little b, little c, little d, little e, and little f in it. And then set C has little x, little y, little z, little w, u, and v. And G maps from B into C. And G sends little a to x, little b to y, little c to y, D goes to Y, a bunch of stuff goes to Y, E goes to V, and F goes to V, right? And then finally we have another set, D, which is the set with 2, 4, 6, 8, 10, and 12, and we have a map, H, that maps out of C into D. And H sends elements of C, like X and Y, to elements in D. So X goes to 6, Y goes to 8, Z goes to 8, W maps to 10, U maps to 12, and V maps to 12. Okay? So the stack is like a stack of, it is a stack of three functions. You send in an X from set A, and F grinds on it. Now it comes F of X. But F of X lives in B. Well, you can drop elements from B into G. Out comes G of F of X, which is an element of C. But remember, G of F of X is G open hole F, right? Well, that element of C can then drop into H, because H maps out of C into D, and we'll have H of G of F of X. And that's an element of set D. Does that make sense?
Yeah.
So if we want to build H of G of F, we're going to follow the elements through this trail. So we know it maps from A all the way to D. Okay, it starts with elements from A, F takes them to B, then G takes them to C, and then H sends elements of C to D. So let's just take a look. Let's start with 1. Okay, so where does 1 go first? What does F do to 1?
To A,
Good. Now we see, what does G do to A?
X.
And now what does H do to X?
So good. 6.
So grand total, 1 winds up at 6. Let's do a couple more.
Okay.
2 goes to,
B.
and what does G do with B?
B go to Y.
Great. And then what does H do with Y?
Y go to 8.
So what's our ordered pair?
To 8.
Yes. You see it, don't you? It's just a fun game. And are you all okay with images and inverse images? Like once you have the set of ordered pairs, we can talk about images and inverse images. Do you want me to drag the file into the chat for you? You want me just to share my screen, Manaya? Test 1 is posted in Blackboard. Let me just show you. Everything is there.
Yeah, I just remembered that as soon as I typed it in. My bad.
That's cool. I mean, gosh knows we've got so much stuff. I mean, we really have a lot of good stuff, right? So test 1, problem 4, it was an argument. And I recommend that you review the video on arguments. There was a short video under video shorts, as well as the lecture video from that day. Okay, there's 2 different playlists where information about this algorithm show up, okay?
Okay, thank you.
Yeah, definitely watch the video short because that goes with in our good stuff folder. There was one of the first things that I put up in the good stuff folder was the algorithm for validity. And these are the notes that go along with the short video. Okay, so there is a short video that explains how this works. So I'm glad you asked. Other questions? Three wound up going to B, which we know went to Y, which went to A.
Well, I need help with test 3, number 5.
Okay, test 3, number 5. So we are using the definition of a partition, and we were told that A was the set from 0 to 50, including the endpoints, and that A sub k was going to be k to k plus 1. And that was for k equals 0, 1, 2, dot, dot, dot. Now you have to understand the definition of partition usually starts the indexing at 1. But when we're talking about the three things that need to be true for a partition P, which is the set of, sets, there might be a bunch of them. The first thing is that each A sub I is not empty. The next thing is that if you've got A sub I and you intersect it with A sub j, that does need to be empty if I is not equal to j. And the third thing is if you take the union of all of the A sub whatevers, it could start at 1, but it could start at 0, up to however many there are. That union has to be all of A. Okay, so we needed to check each property for this collection of these A sub k's, okay? So for one thing, A sub k is not empty for each k. Why? Because for one thing, k is an element of k, comma, k plus 1, right? I mean, it's the endpoint and it's included. Or you could think of taking the average, k plus 1 over 2. That real number is an element of A sub k. Like whatever's right in between k and k plus 1, they're average. Because all the real numbers between k and k plus 1 are in there, including the one that's right between them. So that's another way to think about it. But the point is you had to explain, each of these has something in it. Now, the second property says if we take A sub I and we intersect it with A sub j, is that always going to be empty? Well, let's try it for a couple of different values of k. Like let's try k equals 1 and k equals 2. If k is 1, then we're looking at A1 and it goes from 1 to 2 inclusive. If we're looking at k equals 2, it's A2, it goes from 2 to 3 inclusive. And A1 intersect A2 is the set that contains 2 because they both share that endpoint, and that is not empty. So whereas this property 1 holds because none of these sets are empty, property 2 fails because if you take the intersection of adjacent sets, like if you draw the number line and look at them, we start with k equals 0, so we start at 0, and then it goes to 1. And then the next one picks up at 1 and goes to 2. And the next one picks up at 2 and goes to 3. And you keep on going till you get up to 49, and it starts at 49, and it goes to 50 and includes 50, right? So they intersect here if they're sitting right next to each other, if they're adjacent. So it's not that they all intersect together to be non-empty. No, if you take any two of them, see this says if I is not equal to j, then AI intersect AJ has to be empty. But here 1 is not equal to 2, like our I is 1 and our j is 2. And so A sub I intersect A sub j is not empty. 1 is not equal to 2, right? I is not equal to j. So that property fails. Now the union of all of these, right? The union from I equals 0 to 49 of these A sub I, well, that would be, A0, union A1, union dot, 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 up to A sub 49. Well, let's just think about it. This is A0 right here, is this whole set right there. So A0 goes from 0 to 1 and includes both endpoints, union A1. Well, this next set right next to it is A1. This is A1. All of these, including 1 and 0, 2, 1 comma 2, union, keep on going, and then A sub 49. Well, if you put 49 in for K here, then it goes to 50. So we're going all the way up. And we're taking the union of all of those. Well, that is exactly A. So property 3 holds. Does that help?
Yeah.
And it's the collection. If you put them all together in a collection, A0, A1, up to A sub 49, it's not a partition. Of A because property 2 fails. See what I mean? All 3 properties have to hold. And this would be A3. Other questions?
One last question, and I know you already posted the solutions for the test, but still on test 3, I was just wondering why for number 6D, when we're finding the unions of those sets, I put the square brackets and I know it's supposed to be the soft brackets. So since we've concluded in a sense that that's the union of what we're trying to find from 0 to 5, why isn't it square brackets, and why isn't it square brackets? Yeah.
So this is 5D.
6D.
Okay, 6D. So B sub I is this set, -1 minus I, and then 1 plus I.
Yes.
Okay, so we're starting at 0, right? So when I is 0, what is B sub 0? It's
Correct.
-1 minus 0, comma, 1 plus 0, right?
Yeah. So -1 and 1.
And so when I is 2, 1, excuse me, B1, goes from -2 to 2, right?
Yeah.
You're all soft brackets,
Okay.
right? We're going up to I equals 5, right?
Yeah. And that's gonna be -6 and 6.
So when we take the union from I equals 0 to 5, of the B sub I, it's -1, 1, union. Well, these are nested. Obviously, you know that. I mean, I'm assuming you did a little picture of these.
Mm-hmm.
And the last one is -6 to 6. It includes all the other ones as subsets, so it's just from -6 to 6. There are no hardback.
So if it includes everything in the sets but 6 and 6, -6 and 6.
Yeah,
Okay. Okay.
good, good.
All right.
Yeah, these brackets matter. Soft brackets versus hard brackets, they do matter.
Yeah, I was just thinking since we concluded that that's the union, why is it still soft bracket?
Because the biggest set that we're unioning up contains all the other ones, and it doesn't contain -6 or 6, because we're using the same definition for all of them. None of these have square brackets.
All right. Okay. Thank you.
You're welcome. Endicott, have you had a chance to ask a question?
Yeah, I asked one.
Okay. Did you get all your questions answered?
Mm,
Hold that thought. Angela, did you have a question?
No, I don't have any questions. I was reading over test 3 forms.
Okay. Endicott, was there anything? I'll take one more question from you.
Okay, can we do the about the unique formula in any times n plus 1/2, one of the question. I did it, but like, I don't know if it's right.
You mean factorial?
Yeah,
Oh, no, you don't mean factorial. You mean this, the formula of the sum. Like 600 plus 601 plus 602 plus plus 1,000, something like that.
yeah,
Well, this is the sum from I equals 600 to 1,000 of I. But we don't have a formula for that. Our formula says we have got to start at I equals 1 to use this formula. Okay?
mhm,
So in order to do this, you realize that if we took 1 plus 2 plus plus 1,000 and subtracted 1 plus 2 plus plus 599, then what we get is, I mean, if we take all the way from 1 to 1,000 and subtract the first 599, then that would equal 600 plus 601 plus plus 1,000. Why would we do that? Because these are starting at 1. So we can use the formula. This is the sum from I equals 1 to 1,000 of I minus the sum from I equals 1 to 599 of I. That is the sum from I equals 600 to 1,000 of I. So we can use the formula for these two, but we can't use the formula for that. But we can get this by subtracting. Does that make sense?
yeah.
Good. Well, ladies, I actually have an appointment to go to advanced radiology. Let me stop recording. Nobody wants to know that.